Today we are talking about semi-log plots. These are used to graph exponential functions. So let's consider this exponential function, 2 times 4 to the x. And I wrote out, made a table with some values of x, function values at certain selected values of x. Just to give an idea, when x is only at 7, our function is already at over 32,000. So it would be, if we were going to graph this on a traditional set of axes, a traditional graph, we wouldn't be able to plot very many points, right? We would not be able to plot very many points accurately, right? So semi-log plots allow us to graph all of these values on a single graph. Pretty incredible. I think that this is something new for you. It's something might be a little strange at first. Got to get a little used to it. But it's a very different way of thinking about graphing points. Okay, so we're going to graph these points on this set of axes. And let's take a look. We have on the x-axis, we have what we always see, 1, 2, 3, 4, 5, 6, 7, covers those 8 values up there. But on the y-axis, we notice that there's something very different going on the y-axis. First of all, some lines are further apart than other lines. And this is 0.1 on the y-axis, this is 1 on the y-axis, and this is all the way to 10. Here's 100, 1,000, 10,000, 100,000. The next one up would be 1,000,000. So this is a very different way of thinking about this. We are still graphing f of x versus x down here on the x-axis. This is still x on the x-axis, and this is f of x. But this is very, very different. This is a this is called a logarithmically scaled axis. Sorry, I butchered that. But it's a logarithmically scaled axis. Alrighty. Okay, so let's see. Let's plot 0, 2. If I go to 0 on the x-axis, and I want to go to 2 on the y-axis, here's 1, and here's 10. 2 would be right here. It's the next line up. The next line after that would be 3, then 4, then 5, then 6, then 7, then 8, then 9. And I'm really hoping that we can see this well, but I'm a little afraid of how this is going to copy for you guys. On my printer I can see these lines. Really, really hoping you can see them on yours. Otherwise this might be a complete bust, but we will see. Alright, let's go to the next point. When x is 1, f is 8, so we want to go to 8. So here's 1, 2, 3, 4, 5, 6, 7, 8 is right up here. Okay, when x is 2, we're at 32. So here's 10 and here's 100. So 32 will be on the third line up. So 1, 2, 3, and then just a hair over 30 would be 32. Okay, when x is 3, we are at 128. So here's 100. This is already at 200. If this is 100 and this is 1,000, then 200 would be the next line up. So this is 200. I don't want to go to 200. I only want 128. So about there. Okay. For 4, we're at 512. 512. So here's 100, 200, 300, 400, 512. About there. For the next one is 2047. 2047. Let me scroll down a little bit. 2047. So here's 1,000. Here's 10,000. So here's 1,000 and 10,000. 2,000 would be the second line up, or the next line up. 2047 would be just above that. 8,000, the next point is 8,192. So here's 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,192. About there. And then the last one is 32,768. 32,768. So here's 10,000. I want 32,000. So here's 20,000, 30,000, a little over 30,000. Okay, what do we notice about the graph of this? If I were to try to connect these dots, if I were to try to connect these, how would they connect? They would connect linearly. They connect with a line, and I can see that I was a little off on some of my points. It should be exactly aligned because these are exact values of this exponential function. I was just a little off on my line, okay, or on my points, not on my line. But this gives you, hopefully this gives you a really great visualization of what a logarithmic graph, a semi-log plot, does to an exponential curve. We have an exponential function, but it graphs like a line. And that will happen every single time on these. So in this box, what do you notice about the graph? An exponential graph, an exponential function, takes the form of a line on a semi-log plot. Okay, that is really important. Need you to remember that. Need you to know this. On AP Classroom, I saw lots of problems where if you just knew that, you would get an answer very, very quickly. So know that they relate. An exponential function is in the form of a line if you graph it on a semi-log plot. Okay, so if that's true, we should be able to get the equation of this line. We should be able to get the equation of this line if it's a semi-log plot. So to do this, I'm starting with the function that they gave me. They gave me f of x is 2 times 4 to the x. That's our exponential function. I'm going to find log base 4 of f of x. So it's going to be very easy. I'm just going to take log base 4 of each side. Why base 4? Because that's the base of the exponential. So I'm going to take log base 4 of each side. So I'm going to write this for the sake of your notes, what I'm doing. I'm taking log base 4 of each side. Okay, so we have log base 4 of f of x is equal to, all right, inside here I have a product, so I can write this as log base 4 of 2 plus log base 4 of 4 to the x. Well, log base 4 of 4 to the x is just x, just your exponent. And log base 4 of 2, 4 raised to what power is 1/2? I'm sorry, 4 raised to what power is 2? Well, 4 raised to the 1/2 power is 2. So log base 4 of f of x is equal to x plus 1/2. That's a line with slope 1 and y-intercept 1/2. So I can graph that over here. The y-intercept is 1/2. The slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1, and keep on going, up 1 over 1. And we can graph this On this graph now, we can graph it. And there is a graph of, now this is no longer f. This is absolutely no longer f. This is log base 4 of f. This is still x down here. This axis is still x. This is another way to draw a semi-log plot. This is a fantastic way to draw it if you know the equation. If you know the equation, this is your go-to to graph it. If you do not know the equation, if you only have a set of points, then this is your way to graph it. Let's look at some examples. Or let's look at another example, I should say. All right. Let me scroll out a little bit so we can see more of my page. All right. Let's say that we are given g of x is 9 times 3 to the 2x. And it is not lost upon me that I could combine these and make them a single base. But I'm just going to do it like I did the last time. So I'm going to find the values of m and b that make log base 3 of g equal to mx plus b. And then I'm going to graph it on the provided graph, and I'm going to label my axes appropriately. So I'm starting with g of x. And I need log base 3 of g, so I'm going to take log base 3 of each side. So let's come in, take log base 3 of both sides. If I do that, I have log base 3 of g of x, which is what I wanted over here, is equal to log base 3 of 9 plus log base 3 of 3 to the 2x. So log base 3 of g of x is equal to, okay, what is log base 3 of 9? 3 to what power is 9? That is 2. Over here, log base 3 of 3 to the 2x is just your exponent, 2x. So the value of m is the coefficient of x, that's 2. And the value of b is our y-intercept, that is 2. So the y-intercept is 2, and my slope is 2, so I go up 2 over 1, up 2 over 1, up 2 over 1, etc. And there's my graph. What is this axis? This axis is log base 3 of g of x. The x-axis is still the x-axis. Okay, and number 2. Let's do the same thing for this one. We don't have to graph this time. We're just finding the values of m and b such that natural log of h is equal to mx plus b. So I'm going to come in. Here's h. And I'm going to take ln of both sides. Why ln of both sides? Well, because they told me to. And the base is an e, but basically because they told me to. And if they tell me to, that's exactly what I'm going to do. All right, so ln of h of x is ln of 7 plus ln of e to the 9x over 5. So I have ln of h of x is equal to ln of 7, which is just a number, and plus 9/5 x, right? So m, the slope of the line, will be 9/5, and b, the y-intercept, is ln of 7, which is just a number. I could go and graph that if I wanted to. Okay? All right. In those above two examples, we know the base of the exponential function, so we can graph using the grid that we used from example 1 up here. But if we only have a set of data and we don't know the base, we need to graph on that logarithmically scaled vertical axis. Sorry, gosh. All right. Either way, the exponential function should look linear. That is crucial for this section, you guys. What we are doing is we're making an exponential function look linear. Okay? In the case of raw data where it's experimental data, it may not be exactly linear, so it may only be approximately linear. Because sometimes data does not strictly adhere to a certain function. I am stumbling over my words today. Oh well. Okay. The table gives values for a function that will be corrected on your sheet for a function f at selected values of t. Let's graph the data on the semi-log plot provided, which has the vertical axis logarithmically scaled. We will label our axes appropriately. We are going to be graphing exactly these numbers, so this axis will be f of x. This axis on the bottom will be x. So let's graph some of these points. 0.2. 0.2. Okay. So 0.2. When x is 0, we're at 0.2. Well, here's 0.1 and here's 1, so 0.2 will be right here. Okay. The next point is 2, 1.1. So 2, 1.1. Well, here's 1, here's 2, so 1.1 will be just over that 1. The next point is 4, 5.6. So here's 4, 5.6. Here's 1, 2, 3, 4, 5.6 will be about here. Okay, 5 is 12.8. So here's 5, then 12.8. Here's 10. Okay, here's 20. So 12.8 will be just over 10, right? Okay, the next point is 6, 29.4. Here's 10, here's 20. This would be 30, so 29.4 is almost to 30. Okay, next up is 7, 67.6. 67.6, so here's 10, 20, 30, 40, 50, 60, 67.6 would be in between 60 and 70 there. 8, 155.1. So here's 8, 155.1. Let me come up here. Can I see my data yet? Yeah. Okay, so 155.1. So here's 100. The next line is 200. I don't want to go to 200. I want to go to 155, so about halfway in between here. Next up is 10, 8, 10, so skip one here, 10, 819.2. So 800, so here's 100, 200, 300, 400, 500, 600, 700, 800, close to 800 there, about right there. Okay, next up is 12, 4,350-ish. So here's 1,000. This is 10,000 up here. So here's 1,000. I want to go to 4,350. So 4,000. So here's 1,000, 2,000, 3,000, 4,000, and somewhere in the middle there will be 4,353.8. Last, we're going to graph it at 13. For 13, I need to go all the way to 9,900. So 9,933. That's going to be really close to 10,000. Way up there. Okay, so there is my set of data. Let us, well, first of all, I did what I was asked to do here. Now it says, what does the graph say about the data? Well, the graph looks fairly linear. Okay? A logarithmically scaled graph makes the data look linear. That means that the data is exponential. Okay. Now we want to approximate the values of f of 3 and f of 9. So I'm going to draw a line through my data, and again it's going to be approximate because these are raw numbers, these are not exact numbers. So I'll hit some and I won't hit some. This does look like it's lining up really well, but it's still just the line that I just drew is, it's the best approximation for it. So if we want to approximate the values of f of 3 and f of 9, f of 3 is about what? Well, here's 1, here's 2, it looks like about 2.5. So f of 3 is about 2.5. What is f of 9? F of 9 is about, okay, here's 100, 200, 300, a little, maybe 360-ish. That's the best guess for that. Okay? So these are semi-log plots. Really fun and interesting things.